So the topic of this section is called Analyzing Graphs of Functions. So what we're given is an equation for the function, and then we want to plot the function and to talk about specific features of the function. So let's see what happens. Okay, so the first thing we're talking about is this vertical line test. So in the previous section we said that a function was a relationship where for every value of x there's a single value of y. And the way you do that, the easiest way of doing that, is to plot the function and then use the vertical line test to see that it is a function. So the concept is if you draw a vertical line anywhere in the domain of the function, that you will only cross the function one time. So let me make sure this stylus is working. Here we go. So I'm just going to draw some vertical lines. So, and I'll just take one vertical line and we'll just move it. So you can see we intersect the red curve here. If I move it, then it intersects here, but it only intersects one place. So that's how you can tell whether something is a function. Okay, the next thing is finding the zeros of the function. We've sort of talked about that before, and it's really just the x-intercepts. So what the zeros of a function mean are the values of x where the value of the function is equal to 0. And that has a large significance in mathematics. So if you have a practical problem that you have been able to fit to an equation, the solutions to that equation are many times the zeros of the function, which are the x-intercepts. So what's the difference between x-intercepts and zeros? Nothing. Okay, same thing. So what you do is you set y equal to 0 and then figure out what values of x make that happen. And there are different ways of doing that. If it's a polynomial, a second order polynomial, then you would typically factor it somehow or another. Okay, another way to describe functions besides the whether it's a function first, so that was the vertical line test. Secondly, where does the function intersect the x-axis? So if we look at this third order polynomial, you can see there's 3 values of x where the function equals 0. There's one value of y where the the value that the function crosses the y-axis is called the y-intercept. Now another thing we can do is we can talk about whether the function is decreasing or increasing, and we always answer that question with the assumption that we're moving from left to right. And it doesn't matter whether it's positive or negative. What it means is you're becoming more positive or more negative. So, you know, here, even though the function value is negative, it has a negative y value, as we move from left to right, the value of the function is getting more positive. So it's still negative, but it's approaching the positive axis and it's getting greater towards the positive direction. Now here we have a decreasing function. So it's what's happening is during this part of the curve where the function is decreasing, it can be both positive and negative. The thing is that as you're moving from left to right, that the value is becoming more negative. So even though this is positive, it's getting closer to 0, and then when you get to 0, it becomes more negative, more negative. We reach this point. At that point, then we're increasing again, because even though the function is negative, we're getting closer to being at y equals 0, and then we keep going up. We'll come back to this in calculus. How do you know if a function, besides drawing it, whether it's an increasing or decreasing function? Is there some technique? And there is. Another thing that we don't use as much here in pre-calculus, but it'll be one of the main things in calculus, is where are these points where the function changes from an increasing function to a decreasing function, or where does it change from a decreasing function to an increasing function. These are called local minimums and maximums. So this is a local maxima. This is a local minimum. And those local minimum maximum are called relative extrema. So extrema is, like the name implies, it's the extreme of something. It's, in the case of a function, it's what is the maximum value and what is the minimum value. And in the case of this third order polynomial, the maximum value approaches infinity. This thing will keep increasing forever. And over here, the function is decreasing and becomes more and more negative, and it approaches negative infinity. So those are, we would say, for the domain of this function, that the absolute extrema are negative infinity and positive infinity. But what happens is there are local areas. So right around here, you're increasing and then you're decreasing. And this point where you go from increasing and decreasing, we call a local or relative maxima. And this would be a relative minima because we're going down and then we're coming back up again. So at this local area, we do have a minimum and a maximum. So let's just write that out. So this would be what we would call a relative or local maximum. And this would be a relative or local minimum. And this is a big deal as far as the curve is concerned. Besides just knowing how far does this function go up above the x-axis, or how far does it go below the x-axis. If you knew these points, it'd be great. We're only going to be able to approximate those in pre-calculus, but we'll really look at that in a lot of detail. Okay, then you have symmetry, and the symmetry depends upon whether the functions are odd or even. And as the name implies, odd functions involve an odd number, even functions involve an even number. Okay, the number that's the number that is that we're looking at is the exponent. So something like y equals x squared, that's an even function. That's what we see over here. This is y equals x squared. And the thing about an even function is that it's symmetric around the y-axis, or around some axis. In this case, it is the y-axis. But if you had y equals x squared plus 4x minus 7, that's still an even function. And that's because we look at the exponent of the highest term in the polynomial. Now, an odd function, kind of I guess two functions are odd. Y equals x is just a straight line that goes through the origin like that. So it's not quite as, the thing about odd functions is that typically f of some value x is going to be equal to negative of what f of minus x is. So again, these relate the kind of symmetry here. This is y-axis symmetry. A third order polynomial would have symmetry around a vertical. It still would be symmetry. Well, it's around an origin. It's not necessarily the origin here, but at some point you have symmetry around it, so that, like I said, not only does it go over here, but it flips down there as well. So this is an example of an odd function. Y equals x cubed. So what I said was that if you take the value of the function here, so this is x, and if you go the opposite direction to negative x, and this would then be f of minus x. So this is f of minus x, this would be f of x, and what you see is that f of x equals negative f of minus x, or you could say that f of minus x equals minus f of x. So over here, f of x equals negative f for an even function. A lot of times the function and the function evaluated at the additive inverse location are equal to each other, but here you've got the negative sign involved. Now we're used to looking at x squared functions and x cubed functions, but this is to look at, here's another odd function, and here's another odd function, and what I have written out here is the function. Let me just make that a little bit bigger. So this is the factored version of a fifth order polynomial. I'm trying to grab this thing. There we go. So you got 1, 2, 3, 4, 5 factors, and when you multiply x times x times x times x, you get x to the fifth. These factors are going to tell you where the function intersects the x-axis. So if we go to the graphing program here, and we'll paste in the function that I just had, and I graph it, you'll see this. Looks like a lot of lines. So we're going to zoom out in the y direction. Okay, so this is an odd function. Another thing about odd functions is that as you go to negative infinity in the x direction, you go to either plus or minus infinity in the y direction. And if you go the other direction, you go to the opposite direction. So here we go to negative infinity. Here we go to positive infinity. And I didn't mean to do that. How do I unzoom? There we go. Edit. Okay. So this is an example of an odd function. Again, it's odd because we have x to the fifth power. Now if I take this other function here, which has 6 factors, and I copy that to the window here, because it has 6 factors, it's an even function. And I've got to zoom out here. So let's, there it is. So let's zoom out. So you can see the end behavior for an even function goes in the same direction. So if it's plus x to the 6th, then it goes upward, both to positive infinity. If I were to change that function and put a minus sign in front of the whole thing, then what happens is it goes the other direction. It goes to both, to negative infinity. So besides symmetry situations, another thing is the end behavior of the function as you go to negative and positive infinity in the x direction. So we're going to do some homework. We're going to do some examples. So first, we talked about zeros. So we talked about the zeros of polynomials. For rational functions, a rational function is a ratio of 2 polynomials. There's 2 things you usually have to figure out. One is, where does the numerator go to 0? Where does the denominator go to 0? Where the numerator goes to 0 is where you have the zeros. So even, it doesn't matter how complicated the denominator is, we just look at the numerator. So to be able to figure out the zeros, all you have to do is take the numerator, set equal to 0, and solve. Well, it's just already solved. So the zeros of this rational function is x equals 0. That means that's where this rational function crosses the x-axis. Now where the denominator goes to 0, that's where you have vertical asymptotes. And that's where the function becomes undefined. So let's just plot this thing. So it's x over 9x squared minus 4. Okay. Sorry, I keep missing here. Okay, x divided by 9x squared minus 4. And I plot this thing, and here it is. And what I need to do is zoom in a little bit here. Okay, so there you go. So it's a rational function. You can see that the function crosses the x-axis at x equals 0. So that's the 0. You'll notice these two vertical asymptotes, one here and one here. Those are where the denominator goes to 0. We'll talk about that later. Okay, now here's the polynomial, third order polynomial. So the question is, where does this go to 0? Well, it can either have 1 or okay, so this is a third order polynomial. So you can find the if you can find the zeros of this polynomial. Now we haven't learned, you may have had it before, but we haven't covered it in this class. So we don't know how to do long division yet. So we are going to so this is a polynomial, third order polynomial. And we don't know how to do long division yet, so we'll see if we can factor this. And if you remember back, there was such a thing as called factoring by grouping. So what we can do is factor out, take the first two terms, and you can factor out a 4 and an x squared. So you'd have 4 times x squared times x minus 6, I guess. And then you have these two terms, which you could factor out a -1. So that would be, you get x minus 6. So factor negative out of that, you just get x. Factor a negative out of a positive 6, you get -6. You see you've got these two factors. So this is going to be x squared minus 1, because you've got a coefficient of 1 in front of this, and then you got x minus 6. So one of the factors is x minus 6, and then you can factor the quadratic term. So that's going to be 2x plus 1 and 2x minus 1. And the reason you do plus and minus is because that way you can cancel out the inner and outer terms. So 2x times 2x is 4x squared. 1 times -1 is -1. And then you've still got your other factor there. So what that means is you've got 3 zeros, and you set each factor equal to 0 and then solve for x. So you'll get 2x is equal to -1, x is equal to -1/2. The second factor is this. So you set 2x minus 1 equal to 0, 2x equals 1, x equals 1/2. And then finally you set x minus 6 equal to 0, you get x equals 6. So those are the x-intercepts. And then you can find the y-intercept by setting x equal to 0. So you say f of 0 equals 0 plus 0 plus 0 plus 6. So that's your y-intercept. So if we take a piece of graph paper and we'll be able to draw some of it, but it may not be super accurate. So we have the 3 x-intercepts. Let's assume this goes from -10 to +10 on the x-axis, and from -10 to +10 on the y-axis. So you've got x equals -1/2, you've got x equals +1/2, you've got x equals 6. So there's the x-intercepts. And then you've got a y-intercept of, what do we get the y-intercept? 6. So 1, 2, 3, 4, 5, 6. So the third order polynomial comes up like this, goes through there, rapidly up to there, back down, and then it goes way back down, probably. Again, calculus will allow us to figure out exactly how far this goes down and what point it goes down. It's probably going to be somewhere between, between 1 and 6. Usually a lot of times it's pretty symmetric. Okay, So that's a third order polynomial. Then you got a square root function. So again, we can have zeros, x-intercepts, we can have y-intercepts. So the y-intercept is you set x equal to 0. So you get 3 times 0 plus 2. So the y-intercept is the square root of 2. Then you could find out what values of x does this go to 0. Well, this will go to 0 when the argument of the trig function is 0. So that's 3x equals negative 2. Divide by 3, get x equals negative 2/3. So that's the x value where y equals 0. And so let's take another piece of graph paper here. So what we've got is, and because the square root of any number has to be greater than 0. So what we would say is the range is going to be y has to be greater than or equal to 0. That's just because the square root of anything has to be greater than 0. And the domain is going to be limited by this. So x has got to be greater than or equal to negative 2/3. So that when you have x equals negative 2/3, this argument goes to 0. Okay, so let's go. Again, we'll go from negative 10 to positive 10 on both axes. So we have at x equals negative 2/3, just about here, y equals 0, and then we have y equals 0 at the square root of 2, which is 1.41, and that's just 2 points. And then the thing goes like that. You could pick another number. You could do f of 10. So that's the square root of 3 times 10 plus 2, which is square root of 32. And if you get a calculator and do that somewhere, there it is. So calculator, square root of 32 is 5.65. So 1, 2, 3, 4, 5.65 is about there. So it's gonna go up like that. There we go. Notice the y value is always positive. Okay, now what we have here is a rational function, and we need to know where the rational function equals 0. That's so let's do two things. Let's do the y-intercept first. So the y-intercept is where you set x equal to 0. So this term goes to 0 and that term goes to 0. So what you're left with, f of 0 is equal to negative 9 over 3. This is negative 9 over 3, which is negative 3. Okay, so that's the y-intercept. The x-intercepts are where the numerator goes to 0, so we set the numerator equal to 0. So you'd add 9 to both sides, you get that, divide by 2, you get 9/2. Take the square root, you get x equals plus or minus the square root of 9/2, which is plus or minus 3 divided by the square root of 2, and then multiply by the square root of 2 divided by the square root of 2. And so we get x is equal to plus or minus 3 square root of 2 over 2. So square root of 2 times square root of 2 is 2. Okay, so that's the x-intercepts. The other thing you have is this asymptote. So you find out the values of x where the denominator goes to 0. So you get negative x equals negative 3 or x equals 3. So that's going to be that's a line, vertical line. Okay, so let's grab a piece of graph paper. So let's go ahead and draw that vertical line. At x equals 3, so that's the asymptote. Means that the function does not exist there, but it approaches either plus or minus infinity. We have the y-intercept, which is negative 3, which is right there. We have the x-intercept. So let's plug that in our calculator. 3 times the square root of, 3 times the square root of 2 divided by 2. So that is plus or minus 2.12. Okay, so we've got negative 2.12 plus 2.12 right there. And let's go back and look at the equation. Yeah, so this is there's a couple other things that we're going to learn later, but I'm just going to do it now. What's called the horizontal asymptote, and that's when x goes to infinity. In this case, when x goes to infinity, this whole thing goes to negative infinity. So just thinking here, does this all make sense? You also, what you end up with is slant asymptote as x approaches infinity. Right when x becomes large. So the way you do that is you just do the long division. So you have 2x squared minus 9 divided by, this may be more than they want you to do. And actually what I'm going to do is I'm going to move the negative out front. So negative x plus 3. So you'd have negative 2x. Negative 2x times negative x is plus 2x squared. And then you have negative 2x times 3, so that's negative 6x. Then you subtract that. So you get a negative, so you get 6x minus 9. And then to get to 6x, we multiply by negative 6. Negative 6 times negative x gives you positive 6x. Negative 6 times 3 is negative 18. And then we subtract that, so those cancel out, and you end up with 9 plus 18, which is 9 plus 18 is 9. So this is your slant asymptote. So that's a line that intersects at minus 6 and has a slope of negative 2. So it goes something like this. Okay, so that's the slant asymptote. So what you can kind of imagine here is this thing comes down, this vertical asymptote goes to here, then loops around like that. And then what happens is this comes from this thing. Yeah, I'm just thinking it must come up here. So what it does is this line keeps extending like that. So this ultimately has to go through it has to follow this line. So what it would do is it would what it's going to do is you have to extend this thing down. It actually would come up like this and then loop around like that. So this would approach the vertical asymptote. This would approach the slant asymptote. And let's just plot this thing out just so that I'm not losing my mind. Okay, so here's the plot. So we got 2x squared minus 9. 2x squared minus 9. And that whole thing is divided by 3 minus x. And we graph the thing, and okay, so I must have done something wrong here, because that doesn't look right. It was x squared minus 9. I'm not sure why it's not showing the 2 in there. Well, let's just check to see if we got anything that looks right. Yeah, this is not showing a vertical asymptote. It's just showing a parabola, which is, oh, I know what it is. I forgot this. Gotta go in parentheses here. 3x, there we go. That'll work it out. Okay, so now let's go back to our standard view here. So if we zoom out, you can see there it is. And we'll zoom out a little bit in this direction as well. So you can see this comes down. This slant asymptote goes through x equals negative 2.21. There it goes through positive 2.21. It goes through negative 3. Is that what I said it was? Yeah, negative 3. Okay, yep, goes through negative 3. And then this one loops that direction. That's the little bit there. Okay, so that's a little bit beyond what we know at this point, but you can see the basic idea is to find the x and y intercepts. Okay. And that looks like about all there is for this case. Yeah, this is just an example of a third order polynomial that if you multiply it out, it looks like this, but in its factor form, you see it has 3 zeros. And the question would be, how do you find the relative minimums and maximums? And they have to be between the 3 values where x goes, where the function goes to 0. So the 3 values are x equals 0 for this one, x equals 2 for that one, and x equals negative 3. So if I put those in order, negative 3, 0, 2, there's going to be one relative maximum here, and there's going to be a minimum maximum. There's going to be one there. So with pre-calculus, you just have to kind of try to find something. You probably guess halfway in between, but it may not exactly be halfway in between these numbers, but it'd be close to halfway in between.